Welcome to the Richie Flow Nutrition Podcast. My name is Cameron Borg. On this episode, I had the pleasure of speaking with Bob Fosbury and Scott Zimmerman for the third time. Scott is an optics engineer with over 35 years of experience in the industry and has over 80 US patents. In the last decade, Scott has turned his attention to how light interacts with the body. This has led him to become an expert on the physiology of melatonin and how near-infrared light propagates throughout living tissue. Bob is an astronomer and honorary professor at University College London, where he plays a pivotal role in Glen Jeffrey's lab. Bob is also a key part of the Guy Foundation, where his particular expertise is integrated into a broader and transdisciplinary team with a focus on quantum biology. Bob's work has been crucial in our understanding of tissue transparency and the role of light in life. I'm honoured to have introduced Bob and Scott, as their collaborations have been exceedingly fruitful and continue to forge a deeper understanding of health and disease. I've left links to our previous conversations in the episode notes if you want to listen to our conversations chronologically. Before we start, this episode is sponsored by no one. I do my very best to keep this podcast free of marketing and bias for you, the listener. If you would like to support me, I have linked my Substack below. This is where I share further insights into these podcast topics and provide a depth of information not possible here. With all this being said, I hope you enjoy the episode. Gentlemen, it's great to see you both again in the same Zoom room together. I always learn so much speaking to you both, and it seems a lot has happened since we last got together. So I thought it would be great to sort of touch base again and put some more ideas on the table and think about what's going on. And we were just discussing this idea of photometabolism and the idea that there seems to be this huge coincidence, and of course it's probably not a coincidence, that basically what the sun provides is exactly what we have evolved to use, and plants have evolved to use as well. And this is all centered around this 1 electron volt energy that the sunlight is basically concentrated around on Earth. So did you want to go into a bit more detail about sort of what this means and what the implications are?
Are you asking me?
I think it would be good for you to give a bit of background. I'm sure Scott will jump in when he sees fit.
Okay, well, I think, we think of the Earth as being in the Goldilocks zone or for life. I mean, this is a commonly used phrase now to describe the balance between the amount of energy we get from our sun, our star, and the amount of energy that's necessary to allow life to flourish on Earth. And usually the metric of this Goldilocks zone is normally associated with water. That is, we're living on a planet which is at the right distance from the sun, our star, to allow liquid water to coexist with ice and water vapor. So, in some sense, we are in a band of orbital radius such that water is available as a medium to host life, if you like. I think what we've realized, and the sums that I've been doing over the last few months and so on, there's a much closer relationship between what we're getting from the sun and what life is actually using. Now, I'm not going to talk about photosynthesis because, that is relatively well understood. And photosynthesis, as we know, uses the visible part of the spectrum, which is where the most energy in sunlight is. And for photosynthesis, the solar photon energy is being used directly to create the chemical energy in the sugars that the plants produce, both to build their own structures and also to provide food sources for the other forms of life on the planet. So photosynthesis is plugging into the predominant radiant energy source of the sun, and it's using the visible spectrum where the maximum energy input is coming from. I think what we haven't realized, and only this problem with public health now is bringing up onto the debating table. We haven't realized how important the sunlight is for the inverse of photosynthesis, i.e. the metabolism of the food, of the sugars, carbohydrates that are produced by photosynthesis. And so I think we're realizing that a different part of the spectrum is being used by the whole biosphere. I'm not talking just about animals. I mean, plants as well. Plants have mitochondria. They have to respire. They use the infrared as well. It just so happens that plants get plenty of infrared because they thrive in sunlight, and they don't want too much. So they get rid of some of it by scattering it from their leaves and scattering it down into the forest understory, for instance. The animals actually can use the infrared, and indeed the fungi can as well, I believe. So we have this channel where the infrared light from the sun is providing a rich source of energy, which is almost perfectly adapted to help us metabolize food most effectively. And the numerical coincidences are, I would say, surprisingly close and more profound than perhaps we'd realized before. The balance between sunlight reaching the surface of the Earth and entering the biosphere is amazingly well matched to the stability of the biosphere, the balance between energy coming into the biosphere and the energy going out of the biosphere in radiation at longer infrared wavelengths back into outer space. Maintains the whole balance of the thermal properties of the atmosphere of the planet. So, global warming or heating or whatever, it's an equilibrium state, which demands this balance between energy input from the sun and energy output radiating back into outer space. We've started looking in more detail at what is coming out of the sun in the wavelengths around, or the energies of photons around about 1 electron volt, from about a few tenths of an electron volt up to about 1.5 electron volts. That range is basically in the near infrared. It's centered in the near infrared. The photosynthesis is using photons with energies of 2 to 3 electron volts further into the blue. That's where a lot of the energy is. But the maximum photon number rate, the maximum photon flux coming from the sun, not when plotted against wavelength, but plotted against energy per unit energy, which I think is more appropriate for the biochemistry. The photon number per square meter per unit energy per electron volt is a maximum in the near infrared. And it's a very broad maximum. And it's a maximum in the infrared, regardless of the details of the solar spectrum, because the solar spectrum is close to a black body spectrum. It's close to a Planck function. But there is a distinct difference in the near infrared between the Planck function and the actual radiation from the solar atmosphere. And I'll try and explain that simply, but it's well known to astrophysicists who have to learn about stellar atmospheres. But if you look at stars like the sun, sort of what we call late type stars which are relatively cool, they're different from the much hotter stars, the A stars and the B stars, in the contributors to the opacity of the atmosphere. That's the ability of light to travel through the atmosphere of the star. And it turns out that in sun-like stars, in the infrared, in this near-infrared range of the spectrum, the dominant source of opacity, that's the fogginess of the fog that you're looking through when you look into the stellar atmosphere, that's a minimum at about 3/4 of an electron volt. And that minimum is the result of the behavior of a very simple ion called the H- ion. It's a hydrogen atom which has a small affinity for picking up a second electron. Because a single electron going around a hydrogen nucleus doesn't shield the nucleus very well, because it's all over the place. And so if you put another electron near a hydrogen atom, it will latch on to it with an affinity of about 3/4 of an electron volt. And it turns out that knocking that electron off the H- ion provides the opacity in this near-infrared region. It provides the cloudiness. It's what absorbs the light when the light's coming out of the atmosphere. So it's the origin of the fogginess of the solar atmosphere in this spectral region. And at longer wavelengths, it gets taken over by a different process called free radiation, where two electrons interact with one another. But in this, there's a minimum in the opacity at about 3/4 of an electron volt, which means that you see deeper into the solar atmosphere. So when we look up at the sun, which we can't do because it's too bright, but when we look at the sun, you're looking at about 1700 nanometers, around 3/4 of an electron volt. You're looking deeper into the stellar atmosphere than you are at other wavelengths. And as you go deeper into the stellar atmosphere, it gets hotter. The stellar atmosphere is hot on the inside and cooler on the outside. And then when you go further out into the chromosphere and corona, it gets hotter again. But that's much more complicated non-equilibrium physics. But the actual structure of a stellar atmosphere, it's hotter the deeper you go. So when we look at the sun in the near infrared, we're seeing photon radiation from a deeper layer, which is hotter. And we know that the number of photons, the amount of energy that's coming out of a hot body, depends on the temperature to the fourth power. So it's quite a strong effect. We get more photons coming out of this deeper layer than we do of the slightly shallower layer. And it's quite a marked effect. And that just means that if you plot a Planck function on top of the solar irradiance spectrum, spectral irradiance spectrum, you'll find that in the near infrared, the sun radiates a little bit more than the Planck function does if you fit it at other wavelengths. And it just turns out that when you plot the solar spectrum, instead of against per unit wavelength, when you plot it against per unit energy, you get this sort of mountain-like peak at 3/4 of an electron volt in the number of photons coming out of the sun. It's much more marked when plotted that way. When you plot it the other way, there's a sort of broad, shallow difference. But if you plot it against energy, you see this Everest-like peak of light coming out of the sun at these wavelengths. And that falls essentially right into the middle of the transparency window where light penetrates into living tissue. Not just animals, in all the living tissues. So, whether it's been a long evolutionary adaptation or not, one can only surmise, but it so happens that the peak photon number radiation from the solar atmosphere feeds straight into the biosphere, into those wavelengths that are penetrating deep into bodies. And that energy then becomes available for, interacting with biology in some way. So that's an amazing it's an amazing coincidence that there's a much closer, much more intimate relationship between the light coming from the sun at those wavelengths than there is at other wavelengths. It suggests that there's been a sort of billions of years of adaptation of biology to match the sunlight coming down to it. And this maximum peak will have been true throughout the evolution of the sun. The sun's changed in brightness quite a lot over the lifetime of the Earth, but this opacity minimum in the infrared will have been true for all of that time. So it's an extra source of energy that's been available that can be adapted to. Now, I don't know how strong an argument that is. It could be just a coincidence, but there's been a long time for evolutionary processes to make use of that adaptation. And there's another coincidence, which again seems obvious in some ways, but if you take the amount of solar energy reaching the surface of the Earth in this band where where living tissue is transparent, i.e. from about deep red, 700 nanometers, through to about 1800 nanometers in the near infrared. If you take the energy that's coming from the sun in that wavelength, the irradiance is about 500 watts per square meter. Okay, it's a subset of the solar constant, because we're ignoring the wavelengths where the body is not transparent. But in this tissue transparency window, the energy we get from direct sunlight is about 500 watts per square meter. Now, if I took Scott and I sliced him from head to toe right through his body, while he was still warm at 37 degrees centigrade, he would radiate into his surroundings 500 watts per square meter. So
let's not do that.
I don't know. It might be an experiment worth doing, actually, to convince people.
I don't want to know how you came up with how you know that.
How I know what, not to do it or not? Oh, it's very easy to calculate. I mean, you just take the solar irradiance spectrum and you integrate it between those two wavelengths, and then you take a surface at some 37 degrees centigrade, which is 310 kelvins, which is the number you have to use, and then it's just Stefan Boltzmann's law. You know, it's the Stefan Boltzmann constant times the emissivity, which is close to 1, times the temperature, the absolute temperature to the fourth. It's a terribly simple calculation to do. And if you do that sum at 37 degrees, you will get 471 watts per square meter. So there's this, in sunlight, there's this detailed balance between the amount of sunlight energy reaching your body and the energy that your body is radiating into outer space.
And what I found so interesting about what Bob's talking about is that, you know, when Bob was talking about, you know, when you're in the dark, we still live, we still generate ATP. The body has this particular kinetic temperature, or energy that it's doing. But then when you add in, what hasn't been happening is people haven't been adding in the radiative component. The effect of sunlight is on top of working with, essentially, you've got enough thermal energy to get the molecules going enough to allow the electrons to move through the electron transport chain when you're in the dark, but it takes quite a bit of time relative to if you bring in these higher quality, lower entropy photons. That's it's the photometabolism that Bob's talking about, component. Isn't that a fair way to say it, Bob?
Yeah, it creates a bath of energy. We call it a phonon bath because the energy comes in the form of vibrations, I think, molecular vibrations. And actually this energy, I like to use the analogy, it makes the molecules sing. It creates vibrational states in the molecules and makes them sing. And when the molecules sing, they can interact with one another faster. It speeds up the interactions between chemical reactions between molecules, just like heating them up. But it's a different sort of heating. It's a kind of it's a heating by transferring vibrational energy, and we don't really understand exactly how that happens. We have ideas about why it might happen, but I think the discussions we're having throughout the next few months, probably with the quantum biologists, will hopefully illuminate the kinds of interactions which allow the body to transfer this energy from the photon, the incoming photon. It's worth pointing out that although you think of infrared photons as being low energy photons, if you look at a photon in this tissue transparency window coming into the body, and you compare that with the amount of thermal energy in a molecule buzzing around at 37 degrees centigrade, you know, the Boltzmann energy, the KT, the energy of a 1 eV photon is 40 times as much as the energy of a bumping, you know, a moving molecule at 37 degrees centigrade. So the photons are extremely rich in energy. Fortunately, there aren't so many of them because of the dilution, geometrical dilution coming all the way from the sun. Obviously, if these photons were in thermal equilibrium with their surroundings, you'd be vaporized instantly. Of course, you'd be 6,000 degrees. But the photons that are coming from the sun are carrying large packets of energy that can be deposited in the body and used for these various functions. Exactly how the energy is deposited and transferred to the molecules to enable them to, interact more quickly. If anyone of your listeners knows, just give us a call. But, we have ideas. There are various ideas about how this might happen, but it's something that I don't think has been looked at very closely in biology. The way the energy transfer is made. This energy transfer to water is probably extremely important in biology, and that has been studied to some extent. But the transfer of energy from photons to biology is a subtle process, quantum mechanical process, which I don't believe is terribly well understood.
Yeah, but one of the things that was so interesting, another coincidence, I guess I'd say, is if you look at the electron transfer chain, there's 4 stages. Those 4 stages in general are about 0.4 electron volts. So you have this situation, everybody's been looking for chromophores that are broadband, because you look at Glen's work, he's taken 670 nanometers, he shows an enhanced efficiency of the mitochondria, and with his work, and then there's never other people that are showing it at 1064, and then there's some people that are showing 1270, and there's all these different wavelengths, and everybody's been looking for a chromophore. But what if the real thing is that it's just basic physics? A molecule has these electrons, and has various microstates, or virtual states, that these higher quality, lower entropy photons come in and get absorbed or essentially excite the electron up over the barrier of 4/10 of an electron volt, and that gives you this extra little boost.
Yeah, and that's exactly what you need, is this extra little boost all the time. And I think that we searched for a long time for particular wavelengths that would represent particular chromophores. A lot of early work was done on cytochrome C and cytochrome C oxidase, and so on, looking at the spectrum and trying to decide what absorptions would take place and what it would actually do to the chemistry. And I'm not saying that's wrong, that probably still goes on, but I think the dominant process is a continuum process, which uses all the energy that's coming in these photons in the tissue transparency window, and using that energy for driving the chemistry more quickly.
Yeah,
it's like heating up the body without damaging it in a way.
Yeah, well, it's like, and it's one of the key things of understanding the difference between heat and essentially a photon. It has a slightly different effect, is what I'd argue. But what I think is amazing is if you look at the peak where it's at, and then you start looking at what the electron transport chain did. I mean, the idea that if you wanted, you've got to get 1.6 eV. You got 0.4 4 times 1.6 eV. If I tried to think about a stream coming through a river, and I try and jump that in one jump, I'm going to end up in the water in the middle, not very happy. And maybe one time in a million, I can jump the river. That's kind of what the quantum biologists are kind of saying, because what ends up happening, instead of taking that one big jump, it broke it into 4 different, and whether 3, 4, whatever, but it's 4 right now. And so it's like putting stepping stones across that river. And what I find the most fascinating thing is that has not just allows the probability of occurring more, but it speeds up the whole. It takes it down to a millisecond for those electrons to move across all these different jumps, because if the other way, it could take days. We'd be dead before we got an ATP molecule made. But it
Yeah, I
all
think
that just coincides with that 0.75 electron volt as being it's a little bit, it's got a little bit higher energy, but as far as an efficient transfer, it's just like I say, I think the coincidences are just really starting to stack up. That what we're really looking at is a transfer of energy into the molecules to allow these quantum tunneling effects to actually occur, rather than, and we do fine, we can survive in the dark and with the temperature associated with overcoming, but I bet you can, I'm pretty sure it's less efficient than if we add in the radiative component to go with it. So that's my kind of take on the whole thing.
Yeah, I think the electron transport chain, with its different stages, the different complexes in the electron transport chain, it's a bit like a flight of locks. If you've got you're letting the electrons run downhill through the electron transport chain. But if you let it happen all at once, just set the electron rolling, and it zoomed down all at once, you couldn't probably handle it by the time it got to the end. But actually, it's coming down through a series of locks. It's being stopped, and then they're opening the lock gates, and then it's going down to the next step, and it's going down to the next step. So it's breaking this down into a series of stages, which in a sense seems very sensible, because the mitochondrion is incredibly it contains dangerous amounts of energy. The voltage gradient across the inner membrane of the mitochondrion is about 30 million volts per meter. Now, okay, you're not dealing with a meter, you're dealing with a few nanometers or so. So the voltage is quite small. It's about 200 millivolts or something like that. But the gradients are very high. And if you put these gradients in small-scale structures, you're going to have very, very strong electric fields. And I think, there's a kind of general argument that you will try and break this up to do things in stages rather than try and do them all at once, to avoid these very, very highly concentrated regions of energy, because you can do things like make reactive oxygen species and so on when you get lots of energy together like that. So it seems to make sense in terms of the way to do it.
And the other thing that I think that is really exciting that we're looking at is that when you start looking at the structural characteristics on an optic standpoint, periodicity that's built into this thing, it's also helping out in light trapping in ways that we just are starting to understand. We know that the plants all generate in the chloroplast, a very strong periodicity structure. That has almost nothing to do with the photosynthesis as far as what people talk about photosynthesis. This is an optical trapping effect to get the photons that are necessary, the reds and the blues, to the maximum amount of concentration. It's been happening for billions of years with diatoms and things of that nature, where the structure is actually localizing, enhancing the efficiency of a biological process. And you see those same structures, but as Bob's shown, throughout the cells, they all have these structures. Anytime you see something that is a refractive index difference, and you see multiples of that, you're almost guaranteed that something optically is going on to try and enhance the biological process. So it's like we're starting to learn the biological process, but we need to also throw in the optics side of the things, because it literally is changing the overall efficiency. And literally in plants, they reject the green mostly, and they actually localize the reds and the blues. The same thing I believe is happening in the mitochondria and in the all the other structures within the cells, because as Bob's shown, the the photons are essentially bouncing around and filling up a volume when we're outdoors, and that effectively increases the probability of getting something. And nature will go after 5 or 10% improvement, because it's worth it for survival. If I got 5 or 10s over the guy next to me, I'm going to win. So I think that to me, it's just opening up this huge, beautiful array of all these different effects that the biologists haven't taken into account. But clearly
we have this machine operating in our bodies that we've been blind to. It's a highly tuned machine for harvesting and processing photons to get them into contact with the biological process, I think. And I think the question of comparing the plants with the animals, in this case, if you look at there's a beautiful paper written by the Bristol group about a begonia growing in the forest understory in Malaysia, where they show that the chlorophyll is arranged in the chloroplast in a series of layers, which are separated by around about 100 nanometers. And this sets up a standing wave in the incoming photons, and the maximum amplitude of the standing wave corresponds to where all the chlorophyll is. So you're turbocharging the absorption of chlorophyll in the green. And now, chlorophyll doesn't absorb green very well, but if you work it hard enough, it will absorb energy from green photons, and it will use those for photosynthesis. And this is what this plant is trying to do. It's trying to survive on the green light that comes down from the forest understory. The canopy absorbs the blue and the red that does all the photosynthesis, and the poor begonia sitting down on the floor on the ground only gets green. They say, hey, this green is pretty much useless to me. What can I do to amplify the process? And it does this in this wonderfully elegant way of making a layered structure, a photonic structure, which traps the light, sets up a standing wave, and lets the green light actually do photosynthesis.
I want to make sure I understand this idea about periodic structures and generating standing waves. So in my mind, a standing wave is basically the constructive interference of two waves at a point. So it makes it look like those waves are not moving, but just propagating in amplitude. Is that the right idea?
Well, I think Scott, you're the optimist here.
Yeah, well, I don't know. But no, what happens is the minute you set up a periodic structure, there is a localization of energy. You can literally see a localization of energy. And it's really the concept that's being used for all telecommunication. We built these fibers that have these periodic structures. It allows there to be localization. Some of that can be used to enhance. If you put the right thing in the right spot, you can get an enhancement effect. But in all these cases, you are you're setting up and it's wavelength dependent, from the standpoint of, it can be blue as the blue jay sitting out there and the blue that's reflected off of it type thing. But in the cases that we're seeing with these structures, what it means is the places with higher index of refraction in general have a higher energy density. More photons are ending up in that region compared to the low index. And what's really cool is that, we have to also start thinking about when plants are doing this, they're actually generating gases. Oxygen's being generated. It tends to change the refractive index density of the low areas as well and pump it out and all this other stuff. So there's so much dynamics of interplay between the optics, structures, and the biology. And I think that's what's really kind of what we're bridging right now and trying to understand it, and also pulling in the quantum guys on top of everything else. So it's getting quite interesting, all the different silos and ways that you're playing it. So
I better just take a second here to just sort of backtrack and make sure I understand what we've been talking about from the beginning. So I think what's difficult to grasp is this idea that, we're talking about sunlight providing energy. And I think when most people hear that, they think of energy in the same way that they think of food. And perhaps that's not the best way to conceptualize it. It's not coming down in the form of, carbon structures that can be oxidized in the mitochondria, that type of energy. I think we're talking about the fact that these photons can impart a sort of vibratory energy in the form of these phonons that allow these reactions to basically happen. The obstacle between the chemical step, is overcome by the addition of this energy, and presumably this this energy that needs to be overcome to make the reaction maximally efficient was evolved that way because we had access to this solar radiation all the time. So, there was no need to make it any more efficient than that because we had access to all of these photons. So when we talk about energy coming from the sun, we're not thinking about it in the same way that we're thinking about food. We're thinking about the way these photons are imparting a different type of energy into various structures that aren't necessarily chromophores. Have I got the story somewhat correct?
Cameron, I mean, it's a very important point you're making, and we should make it very clear that in photosynthesis, the photon energy from the sun, it's the photons from the sun that are actually the source of energy that makes the sugars. In photometabolism, the photons are a source of energy, but they're not the source of energy that is being used to make the ATP. They're a facilitator of the process that makes the ATP. So the energy comes from the food, it comes from the photosynthetic products, it goes back into the mitochondrion as food, which effectively generates electrons to go into this electron transport chain. And then the photons from the sun, in this case, they're not providing the energy. The energy is coming from the food, it's burning the food. But those photons facilitate the electron transport down this chain, which ends up making the ATP. So we've used the analogy lubricant before. In a sense, it's a lubricant. It oils the engine. If you consider the mitochondrion as being an engine, it's often called a battery, but let's call it an engine, like a car engine for the moment. You've got a source of fuel coming in to the engine, and you've got to make the engine work to use the fuel, to burn the fuel, to make the energy to drive the car along. In this case, you have a source of fuel, which is the electrons coming from the food that you eat, but the photons lubricate the engine and also cool it, because as Scott has shown in the past, if you have infrared radiation, it seems that you generate melatonin, which is the world's best antioxidant. So, you're sopping up the reactive oxygen species that you necessarily make in the electron transport chain, because it never works perfectly. So you end up making reactive oxygen species, and the melatonin orchestrates the control of the reactive oxygen species that are in the environment of the mitochondria. You need some, but you don't need too many.
Yeah, and I think it's another coincidence that, and it's not. I don't believe in coincidence in this anymore. But the melatonin levels are peaked up during the evening and at night when you're having the least efficient form of ATP generation. Yes, things are calmed down, but the brain is still doing its thing. So melatonin was necessary in order to do that. But I also think that one of the other things that's very important is what Bob's showing. Bear in mind, all I did is I found this graph that the solar cell guys were doing that showed this crazy peak at 0.75. And Bob kind of looked at, well, of course it's got a peak there because of this H minus. But what we're talking about, and if you look at Bob's Herschel talk, the spectrum that's normally shown for sunlight is in watts per meter squared per nanometer as against nanometers. That shows this that everything, all the energy is up in the visible. And unfortunately, everybody is kind of has blinders. They look at the peak first. But all Bob did was change it in different terms. It's exactly the same spectrum, but when you plot it this way, which is more relevant, Watts, what does a mitochondria know about Watts? What mitochondria cares about is electron volts, which is a unit of energy. And all these processes...
Just talk, Bob, so it triggers your screen so we can see the diagram.
Oh, okay, I'll shut up. I'll let Bob show you.
So you see the peak on the... I can't move my fingers, but you see the red peak in the red band.
That's exactly the same spectrum as our same energy densities or whatever you want. It's the same. It's just in different terms, and it shows it's much more relevant. It's exactly like what happened with the photosynthesis guys. They got rid of watts and started talking about photons, micromoles of photons. This is what that graph that Bob was showing is exactly what the people that are doing solar cells with trying to optimize solar collectors. We are a solar collector, whether we want to believe it or not. And so the appropriate way to show sunlight is the graph that Bob just showed you, because that's showing that within an energy range that is applicable to what's going on biologically in the body, that around that 0.75, nature has over billions of years developed processes that just happen to fall in that same region. And the reason is that if they went too much the other way, they do it with chromophores when the high energy stuff, you just fry everything. And they have to have some kind of a process that when there's no sunlight, there's still enough energy through these photon vibration, thermal vibrations to make ATP occur. Less efficiently, but more. And I think that is the fundamental thing that I keep on coming back to is that what we're really showing is that sunlight is helping us generate ATP more efficiently, as Glenn shows, and it's doing it not because it has to decide to find a particular chromophore. It's doing it because we have created this phonon bath, whatever you want to call it, that facilitates the probability of the electron being able to either quantum tumble or somehow get over the barriers that are put in place in the ETC. And I think you'll find that there's probably same thing going on in the brain, same thing going on in all these other different processes. We are designed to operate with this radiative component in our best manner. That's why when you go outside, you're smarter, you're a lot of things. So that's...
Yeah, we need to address this question of what happens in the dark, because it's often the question, we keep saying that if you're in sunlight, all these wonderful things happen. What happens when you're in the dark? And I think this is a very interesting question to address. I think when you're in complete darkness at night, as you should be at night, then your metabolism still works, of course. You're still alive when you wake up in the morning, hopefully. It still works. But actually, if you do the sums, there's not enough energy from the thermal source in your body to get the electrons down this electron transport chain, unless you accept that you can quantum tunnel through these barriers. Because there are these barriers, the sets of barriers that the electron has to overcome before it releases energy at each of these barriers, which pump the protons through the membrane. So it's an energy releasing process. The role of the electrons down the electron transport chain, you're releasing energy into the mitochondrion to pump the protons, but you have these barriers you have to hop across, and in the dark you don't have enough energy to hop across. I said, a photon contains 40 times as much energy as the kinetic energy of the motion of a molecule or an electron. So the only way you can get through these barriers is to quantum tunnel through them. And, I think it's been shown that quantum tunneling, everybody thinks that there's quantum tunneling in the electron transport chain. There has to be. because I don't think you can't make an electron transport chain without quantum tunneling in this way. So we need the quantum tunneling, but that's a relatively slow process. You have to hang around before you get enough probability to jump, to tunnel through this barrier rather than hop across it. As soon as you go out into daylight, you've got this flood of energy coming in. There's no problem getting over these barriers. Suddenly, there's all this energy around. You can maximize the rate of electrons down the electron transport chain. Of course, it's limited by other factors, but you can maximize the rate of the electron transport chain easily when you're standing out in sunlight. In fact, I'd even go further to say, and I had a long discussion yesterday with somebody in the US about this. In some sense, when you're in sunlight, direct sunlight, you are solar powered. You don't need to eat. If you go out in the sun all day, you will eat because you're used to eating lunch and you're used to eating dinner when you get home. But actually, you're getting a lot of energy from the sun. You're getting as much energy from the sun as you're radiating into outer space. And I think this is, maybe not so much relevant to our lifestyles, but there are animals that have these extreme energy requirements. In fact, some of the bird migrations, there's a bird called the bar-tailed godwit, which flies from Siberia or Alaska to New Zealand every year. And it flies 8,500 miles in 11 days without stopping. And before it takes off, it absorbs its inessential organs into its body to provide a fuel source. And it flies for 11 days without stopping eating or drinking. How does it do that? It has 1.5 grams of fuel. It's about a 6.5 gram bird. It has 1.5 grams of fuel, and it manages to fly these huge distances. The reason it can do this, I think, is it's solar powered. It's essentially solar powered. It's getting the energy from the sunlight during the day, and it's solar powered. And there are other examples of this that you hear about. You think it's apocryphal. I mean, there are Indian gurus who say they never eat. I mean, they cheat, I'm sure. They do eat. But in some sense, when you're out in the sunlight, you have much less of a nutritional demand because the nutrition's coming from the solar photons. They're your highest quality nutrient. And, on their own, the solar photons won't do it. You have to have a source of electrons to flow down the electron transport chain. But there are many ways of generating electrons, not only from food. So, I'm half serious about this, but I think we've thought a lot about the possibility of sunlight providing the energy for flight. And there are extreme demands on heavy birds, the albatross and the swan that, weigh 10 kilograms or something. They can only just take off, and yet they stay aloft for days and days. Albatross stays aloft for weeks, and, they're very efficient. They don't use terribly much energy, but, these animals are, to a large extent, I think, solar powered. No.
Well, I just think that the big thing for me is that by switching over, redoing the histograms in the data and moving away from watts into electron volts, it's much more of a true indication of what's going on. I think like I say, I don't believe in the coincidence that it happens to align with a lot of the biological processes so that there's just enough energy or a little bit more energy than needed to cause that particular electron to move. And I would say that that's a more efficient operational point than having a bunch of really high energy photons coming in, because I only need 0.4 eV and I got 5. What do I do with the rest type stuff? And so I think it kind of aligns with what you see in general in whether or not we can survive off of sunlight. I probably could use about 30 days of trying that, but I'll give it a shot. That's better than getting cut in half. So I'll take that one over there.
Where else could we get electrons from? You mentioned that before, Bob. Clearly, we can get them from food. I've heard some other ideas about where we could sort of procure electrons, but what were you thinking when you mentioned that earlier?
I don't really know.
I've heard that because the Earth has an electric field and it has basically free electrons, and if you connect with them, if you stand on the grass, for instance, you're able to take up electrons into the body. I'm not sure if that's been shown experimentally, but anecdotally, I've heard a lot of people say if you're standing on the grass, the wet grass, with no shoes on, and you're in the sun, you'd never feel that hungry throughout the day. But yeah, not sure.
Well, I'm not sure. I think melanin may play a role here at some level. I don't know. I'm not a chemist and I'm not a biochemist, so I don't really know. But I feel somehow that the evidence for being solar powered is actually quite strong, and I'm sure it's a more complicated process than just saying you're solar powered. You're not only using solar photons, but solar photons are a form of nutrition. Well, any photon is a form of nutrition, and if it can be used in the right way, and the body is very, life is very adaptable, and I'm sure life has many ways of making electrons when it really needs them. And I think the extreme demands that are placed on life sometimes are, there are butterflies that migrate a very long way. Your monarch butterflies in the US. I mean, they migrate very long distances in sunlight much of the time.
And most of them, a lot of them have, as you said, have structures that allow for increased radiation and increased absorption, depending on the tilt angle of the wing relative to the sun. There's just so many places that the combination of the optics and the biology are so intertwined. We tend to be reductionist. Oh, it's this optical effect or this biological effect, but in reality, it's a combination. I think is what's important.
Yeah, the butterflies. The butterflies they control their body temperature using sunlight. I mean, there are butterflies which have intensely black patches on their wings, which are 0.1% reflective, incredibly absorbing black, and they adjust the wings as their body temperature requirements change to maximize or minimize the amount of energy they're getting from the sunlight. And they have structures on their thorax which radiate light at 10 microns. So they're getting sunlight into their body with solar photons at 5 eV or something. They're using the sunlight to metabolize and control their body temperature and so on. And the excess energy that results from this, the excess entropy that results from the life process, is radiated into outer space by these nanostructures in the chitin in their bodies. And this is a combination of nanostructures on the wings and the body that are cooperating over a big range of scales to take the energy coming in and balance it with the energy going out. So it's a beautiful feedback mechanism in the way the butterfly behaves to control its body temperature.
And as Bob's shown with some of the beetle pictures and stuff like that, insects are so much more in tune or affected by near infrared in particular because they're smaller. There's you get a lot better penetration or even scatters off of different surfaces. But then that same thing, I would argue, you're starting to see from Bob's pictures of hands and feet and things of that nature, where we need to start to accept the fact that light penetrates deeply into the body in certain wavelength ranges, and the body is using every one of those different photons at different wavelengths for something, whether it be UV or visible or It's not like there's just one magic bullet and you're going to put one particular thing. You need the entire spectrum, is what I believe very strongly, because the minute you take away from that and something, of course, what we're doing now with the LEDs and the window treatments, we're making a choice to essentially remove a critical element that the body, and I strongly believe in, I've been dealing with a cut or whatever. So what do? I put a little bit of, I have a broadband near infrared source and I put it on my cut, and I believe it fixes it up pretty fast, and because I believe that you're wanting to enhance your ATP production and your immune response. So that's my take on it.
Scott, can I ask you a bit more about these periodic structures? You mentioned before about mitochondria exhibiting, these periodic structures, and I think Bob, you mentioned that the endoplasmic reticulum, these foldings, these membrane foldings that we see, act as periodic structures as well. What exactly are they doing, and what are the biological consequences of these sort of light?
Can I before Scott answers, can I just
please
talk about the endoplasmic reticulum?
Yes.
Going back to the begonia for the moment, with a spacing of order 100 nanometers working in the green spectrum. If you scale that up to the near infrared, you get something like 200, 250 nanometers for a spacing, a wider spacing to trap the infrared light. And that's exactly what these, if you look at the endoplasmic reticulum, the structure of the surrounding the cell, the sort of service station for the mitochondria, the linear scale of those structures is for trapping infrared light. So that's just a direct scaling, assuming similar refractive index, contrasts, and so on. So there's a clear shift of scale from the visible to the infrared, shown by the nanostructures in human bodies and the nanostructures in chloroplasts.
Yeah, and the mitochondria, we're just now getting to the point. It's extremely difficult to actually take a picture of what a mitochondria looks without damaging it. And so there's some cases, we don't really know what the structure really looks. There's all kinds of pictures on the web, but as Glenn will tell you, most of them are garbage because they literally, what you do to actually fix the cell or the mitochondria ends up damaging the structure, causing swelling, causing whatever. So we really don't have a real feel. But in general, all these places, every time there's a membrane that has a lipid has a refractive index of 1.46 or something like that, water is 1.3. That's a periodic structure. Index of refraction different. The beautiful thing about it, and I would say that, one of the things I'm starting to look more and more at is that, in the atmosphere, we get Rayleigh scattering. That happens, it has a redirection of the photon, but it happens losslessly because the photon comes in, it is then re-emitted in a random station without a change in wavelength color. So now we've got all these different, all I guess I'd say is that the use of periodicity is the most efficient way for energy to be moved around and localized. It is not getting absorbed. It is, as Bob's pictures show with the hands and the feet, it's bouncing around all these different places. There isn't a color change. It's not like we went like in these other processes where you bring in a blue and you come out with a yellow. You come in with a blue, you go out with a blue. But it's got a momentum shift that's associated, and it goes all the way back to the uncertainty principle that's what's required by the quantum effect. And when you're in order for there to be all these different, do Bob's pictures to actually do that, there has to be a very low loss or lossless scattering effect going on. and eventually finding someplace to be absorbed. But in those scatters, there's no wavelength change. There's no energy really lost. So that's what's allowing.
Eventually, the energy is lost because it has to be. And I think, think of this as an analogy. If you think of your body as a balloon, okay, and you're raining photons onto the balloon, the photons are getting into the balloon, and they're spending a lot of time inside the balloon because they're scattering all the time. They're bouncing off cell walls and so on. So, you know, they're in a sense they're getting trapped inside the balloon because they can scatter so many times. If there were no scattering medium, the photons would go straight through and out the other side. They'd be gone in a fraction of a picosecond or whatever. But you know, they're getting into the body and they're scattering, so they're spending more time in the body. And you're continuing to get you're continuing to get these photons coming into your body all the time. So it's like being in a traffic jam on a motorway. You know, you're traveling down the motorway at, you know, however many 100 kilometers an hour or whatever whatever country you happen to be in, with all the cars 100 meters apart. You're traveling smoothly down the motorway. Suddenly there's a lane closure and you get a traffic jam, and all the cars are 1 meter apart instead of 100 meters apart. But there are many more of them because they're slowing down. And so what happens inside your body, you've got a stau, you've got a traffic jam of photons inside your body. It blows the balloon up. So you're increasing the pressure of photons inside the balloon. And if there's no leaks, where do those photons go? Unless they're being absorbed. And the thing is, they're only very, very weak absorbers inside the body. But eventually, these photons will get absorbed because there's nowhere else they can go. And so what happens is you have a balloon inside your body with a pinhole leak. So the leak allows enough photons to escape from your body to keep the balloon intact. But the leak is feeding energy into absorptions. So you have an equilibrium number of photons coming in and being absorbed. So, you know, the leak corresponds to the rate of photons coming in the end. And so you have a very high density. You can have a high density of photons in your body, much higher density than you're getting in the sunlight, a unit volume of the sunlight coming in, because the photons are spending a long time in your body, longer than they would if it weren't for the scattering. So it's, I think the analogy of the traffic jam is a, reasonable one. You've got the same number of cars coming down the motorway. You're not generating cars, but you're putting them in a volume at high density for a long time until they can escape. They either get out the other end or they get fed up and the drivers walk away and whatever. So the photons that get into the body, although more than half of the photons will not get into the body, they'll get reflected out, and some of them will escape from the body. They eventually get to the surface and escape. But a lot of the photons that get deep into your body, there's no way they can escape other than to give up their energy to an absorption. And the absorption is very weak. But that's fine. You need weak absorptions in order to get the light deep into the body. So, it's a clever process in a sense. You accept that you only have very, very weak absorptions, but you have efficient scatterers inside your body, like cell walls. And the weak absorption allows you to get the photons deep into the body, but you still absorb them because there's nothing else that can happen to them. They're trapped in there. So it's a very, very clever way of getting photons deep into living tissue. That's why it's so different from plants and leaves. The leaves have strong absorbers in them to absorb the light straight away. The chlorophyll absorbs the light straight away and makes the energy to do your photosynthesis. But in the body, ostensibly, there's nothing to absorb the photons, so they just get into the body. But once they're in the body, they have to find the weak absorbers, and they do, and they transfer energy to the molecules.
Yeah, it's kind of like what you see when you have a snow and a black asphalt place, and you have beautiful white snow, but then as the sun shines on it, eventually you start seeing the dark little specks because they get radiated, heated up, but the snow is still around it. So, one of the things that this is a very not well understood, but a very, you can go and design solar collectors that have some level of diffusion built into them or scattering built into them to get them to spread out a certain way. And Bob's shown it with like the mushrooms, where they're look white, but when you look in the infrared, you see that the infrared is actually funneled down in to enhance the spore, give more energy to the areas where they have spores because of the optics of how their surroundings are. So, I mean, we are a solar collector. We happen to be a diffuse, very complex solar collector because there's some wavelengths where almost all the energy is absorbed just in the outer 50 microns. And then there's other areas where it can go inches into the body. And as Bob's saying, bounce around for an extended period of time. Well, optically, we use that we take an integrating sphere, we take a laser beam, shoot it into the integrating sphere, let it bounce around a bunch of time. What happens? You get this new distribution of energy, and it's a way to deal with coherence, take the coherence out of the system. So, you're taking some state, some high quality, low entropy, and you're converting it into a lower entropy state by taking something away. But you're doing that essentially in a lossless manner, because the most reflective thing known to man is Teflon with a bunch of air in it at a thickness of about 1 or 2 microns or 1 or 2 millimeters, because it allows eventually all those photons bouncing around in that scattering mechanism either make their way back, out of the structure because they don't have any choice, in the carrier.
Yeah, the integrating sphere is a useful analogy I've used. I've got an integrating sphere. I can show it to you, actually. Hang on just a moment.
Show and tell.
Yeah, that's right. Bob's got he's got to get his Stirling engine out too. We need that.
Yeah, I've got that. This is an integrating sphere. It goes on a spectrometer, and it has you see on the top, it's got a hole, and that hole has a white interior. So there's a white sphere, a highly reflective sphere of white inside there. And what happens, I've got there's a tiny little bulb in here, a little P bulb, just a millimeter long, with a tungsten filament at about 2,600 kelvins. And that fills the sphere with light. It's led into the sphere in a special way, a very efficient way. And if I block that hole with another slab of PTFE, the energy inside that sphere the photon density inside the sphere will be amplified by a factor of 20 or 30. So it's incredible density of photons in there. And if I put my radiometer over that hole when it's illuminated, that tiny P bulb is producing a light which is bright as sunlight. The irradiance coming out of that hole is like sunlight when I've switched this sphere on. And that's because the density is being built up, the photon density is being built up inside the sphere. So this is, in a sense, it's an analogy of the inside of our body. Instead of being a sphere with a reflective surface, it's just a reflective lump of stuff, which scatters very efficiently. It's a lump of white material. The inside of your body in the infrared is a pure white. It's an extremely efficient scatterer. And a mushroom is an incredibly efficient scatterer. If you take a mushroom and cut it, it's incredibly white. And it's a very, very efficient way of scattering light down into the spore-producing bodies. So, for people who are familiar with looking at things in the visible, which we all are, you don't see this at all. So you never see this phenomenon. If we had infrared eyes, which we can't possibly have for physical reasons, we would see that light in the infrared inside solids like wood. And I've got a picture of my finger in my lecture. It's So it's this light from the integrating sphere shining through my finger. And you can see this, my finger is glowing red. Now, everybody would say, I think almost everybody would say, it's glowing red because hemoglobin, blood, is red. And it's not. It's because it's the setting sun. You could take all the blood out of my finger, it'd still look red. I can put a sheet of bamboo wood on over this integrating sphere and it glows red like the setting sun. It's a phenomenon of scattering. It's like the red of the setting sun. It's like, many things that are red because of scattering processes, because you tend to scatter more in the blue than you scatter in the red. So the red goes further, deeper into the object. So we're not familiar, all these processes of getting light into the body, we're really not familiar with because we've never seen it. If I put a mushroom on this integrating sphere, it glows red. I've got pictures on the web. It just glows red because the red light is getting into getting deep into the material.
Yeah, but I do think that brings up the other thing I was hoping we would get a chance to talk to is the what you're finding with the scatter in the atmosphere and the blue and violet character, because you're talking about twilight.
Yeah. My favorite subject, twilight.
But I think it's an important subject because it's really calling into question some of the assumptions around circadian and its effects. And Bob, do you have that graph that you can show?
I do. Twilight was not understood until 1950. The color of twilight was absolutely not understood until 1950, when there were experiments done using Nazi rockets from the end of the Second World War. The Americans nicked a load of these and took them to White Sands and used them for studying atmospheric processes by sounding rockets for studying the atmosphere. And at the time, the theorists who were working on the theory of Rayleigh scattering in the atmosphere couldn't understand the brightness of the twilight sky, or the brightness of the Rayleigh scattered sky in particular, but especially at twilight. And so they sent up rockets to try and measure the Rayleigh scattering at high altitude, and they couldn't reproduce the results using models, the Rayleigh scattering models. And it was someone called Hulbert, who was working at White Sands at that time, who realized that it was ozone gas in the atmosphere that was absorbing the extra light in the visible spectrum. So you were Rayleigh scattering very strongly, but all the green, the yellow, the orange, and the red was being absorbed by the ozone gas. And so the color of the twilight sky, clear sky, the color of a clear twilight sky in the zenith at sunset is a deep metallic purplish blue, very deep, dark, very characteristic color. And that's due to ozone and gas. If you took the ozone away, the color of the twilight sky at sunset would be a sort of grayish straw color. And so the nature of the twilight coloration is very special. It's the most extreme change in color of daylight at any time during the 24-hour cycle happens at twilight. And that's because the blue of the sky, we're talking about clear skies, the blue of the sky is Rayleigh scattering in the daylight. When the sun gets at or below the horizon, the blue of the sky has very little to do with Rayleigh scattering. I mean, it is driven by Rayleigh scattering, but the blue of the sky is predominantly due to the absorption of ozone gas in the ozone layer. So without life on the planet, we would never have this dark purplish blue sky at sunset. If you took photosynthesis away from the planet, that color would be a kind of straw yellow, grayish straw yellow color. And similarly with the air glow that you see in very dark sites, it's a color which looks like the aurora, and it's in fact the same kind of emissions as the auroral emission. It's mostly the red and the green of atomic oxygen emitting. The air glow is emitting light which was the oxygen atoms are accrued during daylight and stored because they have metastable levels in the atom, and they emit them gradually during the night. And if you look at these wonderful photographs they take at astronomical observatories at night, you see this green and red glow on the horizon, which looks like the aurora. And it is like the aurora in the sense that the mechanism that emits the light is similar, but it's driven differently. It's driven by sunlight during the day in the case of the air glow. And this is beautiful. I mean, I have pictures of this emission in dark sites, and it's absolutely beautiful. But it's only there because of photosynthesis, because without photosynthesis, you wouldn't have oxygen in the atmosphere and you wouldn't get these wonderful colors. So there are all these very obvious biomarkers in the sky, which we don't realize are biomarkers. I mean, the color of the twilight sky is a biomarker. It's there because of life on the planet. The color of the air glow is a biomarker. The color of the aurora is largely a biomarker as well, because, you know, that's oxygen in the high atmosphere, which is largely due to photosynthesis, not entirely, but some of it's due to the dissociation of water, but largely it's due to photosynthesis. So, you know, this coupling of sunlight with life is so fundamental and it's so close. And you know, this is what we've been discussing this afternoon so far. It's a very beautiful process, which we've really been rather blind to, this close coupling of the sunlight with life and the biosphere, and, you know, with our own bodies as well. We are part of the biosphere, of course. So it's very difficult to look at, but it's a sort of very interdisciplinary thing, because, you know, it has all these components in it, you know, the physics of the aurora, you know, the structure of the solar atmosphere, the structure of hemoglobin and chlorophyll and biochemistry and biophysics and so on. It's a very interdisciplinary environment. And I'd like to make this point very strongly. The reason we have one biologist in our team. We have a fairly large team now. We have one biologist. It's not all biology. It's many things coming together. And in fact, there's a very close relationship between astrophysics and biology, which I think has not been realized, because when we start talking about light, the interaction of light, starlight, with nebulae for astronomers is bread and butter. You know, we understand how to model the interaction of light from a star with the atoms and molecules in interstellar gas. We can model this in great detail and do so all the time. In the case of biology, we have the case of sunlight out there interacting with the photosynthetic process, but also with the photometabolism process. And those processes are very, very similar to the interaction of light with a nebula. So it's the same kind of mathematical structure you would use to analyze the light with biochemistry as you would with the analyzing the light coming from the star and reaching a nebula. So, you know, there is astrobiology is a very powerful subject now. There's lots of funding going to astrobiology because these two subjects seem to link quite closely, and with very similar mechanisms involved. And that's why we need a very interdisciplinary team to understand. I mean, I can perfectly happily admit to being rather ignorant in biology and biochemistry, but it doesn't matter, because I think about other things that the biochemists and biologists don't think of. So we have to bring these people together, and we have to look at it as a multidisciplinary problem. And I think that's why we're making this progress at the moment, because we have a very multidisciplinary team. An optical engineer sitting just below me on the screen, maybe just above me on your screen, I don't know. But whatever.
Yeah.
And we have a visual neuroscientist, and we have lighting engineers, and we have all of these people working on engineers, all of these people working on the same subject, and it's very important, I think.
Yeah, but I think that also the reverse side, what we're learning, there's been a kind of like a ignorance. I don't mean that nastily. I just mean it from an inability, lack of understanding. It's like when we're talking about the Rayleigh scattering. I don't think most people don't realize that the blue of the sky, the same thing's happening in the UV. And what does that do practically? What that does practically is that it means that our atmosphere is pumping UV into all different directions, coming from all different directions. So there's not a shadow, so that there is UV going into most places and having an effect on the pathogens, having effect on us, our ability to generate. So in a lot of cases, and that's where some of the models that Bob's done about twilight are, I think, quite interesting, because the premise for most circadian is that you want to get rid of 300 or 480 nanometers when it gets dark. But yet in nature, according to what Bob's done, you see that there's all this blue and violet that just happens to almost perfectly align with the melanopsin action spectrum with peaks at 480 nanometers. So it's like nature is providing at twilight, as the sun is setting, nature is providing this blue marker that we have a chromophore, but that chromophore is actually looking for 480 and finding 480, because as you move in, that's a much more reliable, I think, marker. Is that a good way to say it, Bob? More reliable marker of sunset, or than looking at a red sunset. So
yeah, the sunset twilight is incredibly blue, whether it's cloudy or not. So the brightness, the change in brightness at twilight is a poor quality calibrator of the circadian clock, whereas the color of twilight is a very powerful, strong, precise marker of the circadian clock, because it's always, the twilight is always very blue, because it's like a filter. It's a filter above all the clouds. That's the point. So everything that's coming down through this filter is blue. So even if it's scattered off clouds, or whether it's coming directly from the from the sky, it's always blue, because the filter is way above all the clouds.
Do you have that graph?
Yes, I do. I'm trying to think if I could show you a clear copy of the graph. I've got it in my notebook. I guess I could share my screen. Can I share my screen?
If you want, you can send me an image of it later.
I'll send you the image. Yeah, I'll send you the image.
I'll put it in the screen so you can talk about it, and I'll put it up on the screen.
I'll say send image in my note. Send twilight. But
I'll just interject here, because I think it's interesting that the conventional idea is that as the sun is setting, the relative abundance of blue, or short wavelengths in general, goes down as the sun sets, and you're basically just left with the yellows and reds, which is why everyone wants to block out blue. But what we're saying is a bit more nuanced here, is that you actually get quite a strong blue signal at twilight. That maybe
it's not quite strong, it's totally dominant. The skyline is incredibly blue. Look behind you at sunset. Everybody looks at the sun and say, oh, it's lovely and red, and so it's all infrared. That's bullshit, basically. Look behind you. Yeah. The whole sky is blue. The thing that Scott is trying to get me to say all this afternoon, and I haven't said it yet. If you look at the UVB, the thing that generates vitamin D, the part that very close to the atmospheric cutoff, around 300 nanometers. If you look at UVB coming from the sun directly, when the sun gets below an altitude of about 35 degrees, the UVB goes essentially to zero. So in the winter, these are latitudes, we get very little UVB from the sun. And everybody says, okay, we get in high latitudes, we get no UVB, but they don't add from the sun. Actually, we get loads of UVB from the sky, because the sky doesn't change very much as the sun goes down. It doesn't change very much in brightness. It's still scattering very strongly at higher altitudes. it's still scattering light coming from the sun, even when the sun's low in the sky. And that that scattered light is very rich in UV. And if it comes down vertically through the ozone layer from high altitude, although the high altitude scattering is relatively weak, the whole sky is radiating UVB towards you in the winter. So you've got plenty of UVB out there. It's so cold that you're covered up with clothes, so you can't make use of it. If you were naked in the winter, you would get plenty of vitamin D from the sky, especially if you're outdoors all the time.
When you were telling me this last month, I think it was, I almost fell off my chair because it goes completely against what the standard narrative is, and it makes me wonder about pigmentation in traditional populations in northern parts of the world, like in Scandinavia, where they're still extremely pale, whereas the Inuit people in Alaska and Canada actually have the capacity to be quite tan. And I wonder, if there is UVB available year round from this scattering, how do we explain the differences in pigmentation between these populations? I presume there's large genetic differences as well. But is melanin not cropping up in these Scandinavian populations for a specific reason, or?
Well, that's an interesting question. I think let's go to the southern hemisphere a moment and look at the Fuegian Indians in Tierra del Fuego. When they were first discovered, they were prancing around at temperatures around freezing, naked. Okay, so they were living essentially naked, but they used fires to warm themselves up all the time. Fuegian Indians, they had the advantage of skylight, and they also had the advantage that there was a big difference between their body temperature and the temperature of their surroundings. And if I give my my human thermodynamics lecture at the moment, if you're sitting in a room, which you're doing at the moment, we're all doing at the moment, our body temperature is close to 37 centigrade, and the wall temperature in our rooms, I guess, is close to 20 degrees. Okay, so we have a 17-degree difference between our body temperature and our surrounding temperature. Now, if you look at the theory of Carnot heat engines, the maximum efficiency of a Carnot engine with a temperature difference of, 17 degrees is about 4%. I can't remember exactly what it is, but it's 1 minus the temperature of your surroundings over the temperature of your body. Okay, and if it's a small difference between those two, and those temperatures are not in centigrade, by the way, they're in absolute. So you can make them absolute temperatures first, but 1 minus T surroundings over T body, T engine, whatever. So we in our offices and rooms have a maximum production of useful energy, like energy we can use to move around and think and so on, of around 5% of the amount of energy we consume through nutrition. So 95% of the energy that we eat comes out as waste heat, not useful for moving. So we run on a very small fraction of the. And you look at your step counter on your phone, and they'll say you've used up a small number of steps with useful energy, and you've used up a very large number to generate waste heat. If you're a Fuegian Indian at 5 degrees centigrade, you've got a much bigger difference between your body temperature and your surroundings. So you can generate a lot more energy. You can generate, instead of 5 watts, you can generate 13, 14, 15 watts of energy. And so the migrations to high latitudes have exploited this thermodynamic effect, pure thermodynamics. I mean, you can't get around it. It's pure second law of thermodynamics. if you're digging canals or building railways like the navvies in Europe, you're working a lot of the time under an open sky and in the outdoors. You've got a much bigger difference between your body temperature and your surroundings than you would have if you were in an office. And so those guys ate huge amounts of food, and they generated lots and lots of energy to move lots of earth around. And that's just a thermodynamic effect. So in a thermodynamic sense, you're better off in colder climates. And the people who moved to Arctic regions perfected the idea of clothes where you can insulate your body to stop losing all this heat, but you still have parts of your body exposed to very cold temperatures. Inside of your lungs, there's a huge area inside your lungs. You're breathing in every minute. You're breathing in, and you're exposing this huge area to a low temperature. It means you can generate much more energy from your useful energy from your body than you can at low latitudes, where you can never get this contact with the cold surface. And if you look at the history of the Industrial Revolution and so on, why did all these things happen at mid-latitudes? They happened at latitudes where there was a lot of physical energy available. Your steam engines, were working in a colder environment than they would be at low latitudes and so on. So there is this thermodynamic effect, which is very, very important in how much energy we can generate.
Yeah, and I think the other thing is that what it's really showing is that we need to understand the energy sources and the energy sinks that are going on. And as Bob was showing with, I see your little heat lamp over there, and the effect of using it. You make the comment that we need to quit wasting high quality, low entropy photons for and for just heating things, rather than letting that go into the body, do stuff, and use that higher quality input into the body and get rid of it in the most efficient manner, I guess is what I'd say.
Yeah, I think this is our advice to the lighting industry, is that we have all this problem with tungsten filament lamps, which we know are good for health but bad for energy efficiency. What I'm saying is you take these lamps, the tungsten filament lamps, and you run them at lower voltage than you do for lighting, and you take the energy from your heat budget. You don't take it from your lighting budget. You don't call it lighting, but you feed the light through the body, through the occupants of the building. You feed it through the body as light bulbs or whatever, and you still get the heat out. It's just that you get all these high quality photons going through your body, enabling your body to do all the things that it needs to do. That the high quality nutrient, the photons coming from the light bulb are very high quality nutrients that allow us to live efficiently and effectively. And we still get the heat out. So, in the winter, certainly you can divert some fraction of your building heating budget to making light at least a temperature of 2000 kelvins. So never use electricity to heat a radiator on the wall, which radiates at 50 degrees centigrade. It's a total waste of a high quality energy source. Use that electricity to make infrared light at least 2000 kelvins. It will get into the body and make your body healthy. And you won't be wasting any heat because the heat will come out. It just comes out of the heating budget rather than the lighting budget. You can argue about it in your building administration, but that's what you do. It's crazy to use high quality energy to make high entropy heat, heating water.
That to me, I think is one of the fundamentals. I mean, there's about 4 fundamentals that are going on here all simultaneously, but I think that realization that we are taking really high quality electrons and electricity in the wall plug, and we're converting it into very low entropy, useless.
High entropy.
Oh yeah, I'm sorry. Yeah, high entropy. Useless, not useless, but we're not taking into account, as I said, the source and the sink and the importance of that delta and how we do that transformation from a low entropy to a high entropy, and take advantage of, it's unfortunate, I've been looking at the various ways that how you construct a home that has at least some portal out to the real world. And that's kind of, there's certain things that transmit all the way out to 10 microns, if certain polymers and things of that nature. There's all kinds of opportunities to do it. And so that's why, but I did want to, if I could, I'd like to go and jump over to a little different topic for a sec.
Please.
I've been, I think tied into all this is that people are going to start to get more and more knowledgeable about this issue. People are going to have access. You see what's going on with all the biosensors and things of that nature. So what I've been doing also on the side is a little bit of looking at how some of these new biosensors that are coming on the market are giving people the ability to look at the melatonin, cortisols, IL-6, TNF, alpha in real time. What's been happening in the past, and one of the reasons I think that people haven't really looked at this area as much as they should, is that we've had a lack of the ability to really in real time measure stuff. A lot of stuff what we're talking about is a non-equilibrium state, a transient response. So there's some new sensors out there now that I've been working with, and it's just really fascinating to watch because it's a sweat sensor, and it's measuring every 3 minutes these four things simultaneously: melatonin, cortisol levels, IL-6, and TNF alpha. And while you see the general trend that is circadian of melatonin and cortisol, you also are now, because it's sampling every 3 minutes, you're seeing the transient responses. And so there's a whole new world going to be coming out, I believe, here soon, where people are going to be able to say, oh, I sat down and I watched TV at night. All of a sudden I saw my cortisol go up, boom. And, above the baseline, turn the TV off, it goes down. This is happening in minutes, literally in minutes. And, you go out and you eat something and you see the cortisol levels go up. And then all of a sudden you see, if it gets to a certain point, a melatonin spike comes. Where are they coming from? What is how's this happening? So I think that what we're going to see is that, part of the reason is we haven't been able to see. There's also new sensors coming out that lets us look a little bit. Bob's hopefully going to be getting a new radiometer that gets them out to 1700 nanometers or things like that. We've had this problem where, from an engineering standpoint, if I can't measure it, I can't do anything. And so now we've got these whole new set of tools that are coming out that I think are going to redefine, as Bob's saying, lighting and heating. They're, we need to quit keeping them in separate silos. We need to look at them jointly and how they're affecting all these different parts of health. And, people are having continuous glucose monitors. People are doing all these things and once we start seeing those effects, then I think we'll be able to more optimize our indoor spaces and our lighting. And I really do like the idea of eventually getting lighting and heating all together in one thing, and then maybe even bring in some fresh air characteristics, because there's a lot of benefits associated with that I think we've underestimated. So, that's just my little 2 cents on where I think what's going to make the difference, because it's been very frustrating over the years that we've been talking about this, that people don't notice, they don't care about. And I think that once they can see a little number and it means something, or, put the little sensor next to a window and, hey, this window's letting in a bunch of near infrared, this one's not letting in, then I think you're going to start to see more people responding to, well, what does that mean? I mean, literally, I can go and get on a treadmill with one of these sweat sensors, and I can see, boom, within a minute, I can see that thing is going up. The cortisol level is going up. You go up too far, and all of a sudden the melatonin starts to come up. They're slightly offset in time, but we're talking about, I keep on saying what we've been doing for years is we have a tennis ball in our hand, we take a picture, we throw it up in the air, we catch the tennis ball, we take another picture and said nothing happened. That's not what's going to happen here before long, because now with this high frequency sampling technologies that are coming on, I think you're going to, that will then open up. We're starting to have people that are trying to optimize for athletes and things of that nature. Then I think all of a sudden people will start to care when they actually get a number to go along with it. Anyway, that was my little sidebar.
It was definitely one of the things I wanted to ask you about was the sensors, because not only does it seem that this circadian story is getting a little bit more interesting, because now, it's becoming abundantly clear that the relative abundance and the spectrum that we're getting at twilight is maybe not making the original story so cohesive anymore, and that perhaps blues and violets are actually playing quite an important role in triggering that transition from sort of daytime activity to nighttime activity. And it's very well understood now, I think, by most people that melatonin is not just a pineal characteristic. It's happening at a subcellular level. And, these real-time sensors are making it clear that melatonin is very dynamic, and it's not the hormone of darkness like it used to be considered. It's much more involved than just being the hormone of darkness. So are you aware of any circadian people who are, looking into this?
No, I mean, the sensor I'm dealing with isn't really on the market yet, but to me, it was just absolutely fascinating to see, because it's been my pet peeve about the circadian is they'll go and put something in the dark and measure it for every 4 hours or measure it every hour. And you can clearly see, but you're missing all the other interesting structure. I did one where I went to sleep and I intentionally woke myself up in the middle of the night. And then I went back to sleep after a while. And what you see is this nice melatonin ramp up. And then when I woke back up, you get a series within the time frame I was awake, you get a series of these cortisol spikes. So, and people have known that the cortisol is administered in pulses. But then when I fell back asleep, those pulses went away, and it just had the nice melatonin drop off until morning when cortisol came back up and started pulsing. But the dynamic or transient, it's going to be hard because there is so much noise going on. So many things are affecting those levels, and even in sweat on a minute by minute basis to guide or use it as a tool on a continuous basis. But when you start seeing these transient responses and the displacement of where did that melatonin spike come from? What generated that? And that's on a systemic level. What's happening on a local level? So I think that it's one of those things that's going to take a lot of research to understand, what it means. But the existing circadian, I would make this statement just to be a pain in the rear. The existing statement, circadian stuff is just wrong. And it may be part of this discussion, but if you got this baseline, and we're talking about huge shifts depending on the particular stressor that you're going on, whether it be exercise, sex, whatever, you're having huge changes in these hormone levels in the sweat itself. Then things we're oversimplifying it by having, and that's what I thought was so fascinating about Bob's model, where he looked at the integrated total, and all of a sudden it's not just a little bump, it is the dominant peak, and it's exactly at 480 nanometers, exactly where the peak action response is for melanopsin. So it's like the body has been actually picked, he's trying to use that 480 to, as Bob says, make a more accurate gauge of what's going on. So
might this suggest that people who are deliberately blocking out those wavelengths of light, as the sun is setting, to sort of cue this, sort of circadian healthy lighting, they might be doing themselves a disservice by sort of missing this blue peak, this dominant blue peak that exists at twilight.
I'll let you have that one, Bob.
I think the data speak for themselves. I don't have to say anything.
Yeah.
The fact is that twilights are very blue. We've known this. I mean, the French artists knew this at the beginning of the 20th century. The blue hour. Picasso, they used to love the blue hour because it was so blue. The thing is with the blue hour that it happens right at the time where you're transitioning from cone to rod vision. So you have no color sensitivity. So you don't realize that the twilight is blue. It just looks darker gray. But if you take a picture with a modern color camera and you keep the white balance on fixed daylight, you will be amazed how blue the landscape is half an hour after sunset. Yeah. It's incredibly blue. You'll think something's gone wrong with your camera.
Yeah, and the optics.
We've known this. We've known this forever.
Yeah, and I guess my thing is that, and with all the blue blockers and the red, people putting red lights in, if it works for them, fine. But that's not really based. I think it doesn't seem to be based on real science. It's based on, if you have a terribly toxic light source like an LED, you probably do need to try and tone it down a little bit with some kind of blue blocker. But I keep on saying, it would be a terrible shame that everybody went through life and looked at Starry Night by Van Gogh and with blue blockers on. It's just, and we're giving up. I was reading a storybook to my grandchild or whatever at night, and there's no blue content in the pictures. Why do we have to sacrifice information content just because we put in a light source that is so way off the charts wrong that, I don't remember a lot of these problems when I had an incandescent light bulb. That's all.
If I'm at the risk of instantly generating millions of enemies, I would just note that the dynamic range of skylight from sunlight to darkest dark sky with no moon is a factor of 1 billion. Okay, 1 billion. A blue blocker on your sunglasses or glasses will reduce the amount of blue light by, 20%, maybe 30% extreme. And the colors that you see will be weird because you've lost all the blue. That's completely irrelevant to a dynamic range of 10 to the 9. It's, blue blockers, I don't know where the idea came from. It just doesn't make any sense to me at all.
Yeah.
Completely.
Yeah. You can give your address later. Wow.
Yeah.
Right. But I've been concerned about blue blockers for a while now. I wrote an article about how I thought, being exposed to monochromatic light, whether it's, red or green or whatever, could have untoward physiological consequences that we're not aware of. And, ever since I've got your bulb, Scott, I've just been using a combination of that and some other incandescents and candles. And I prefer not to wear my blue blockers at all, to be honest, because I feel like I do better without them. And, that's just an anecdote, but I completely agree with where you're coming from. I think we'll start to see more people come to terms with the fact that, there's plenty of shorter wavelengths in fire, but we know that that's probably the best thing to have before bed. And I think, the fact that there is a huge portion of light after the sun has set that's a blue, the major portion, I actually want to talk to more circadian people about this, because it seems like they're either unaware of it or not sure how to integrate it into their ideas.
Let's put it in another. I'd put it in different language. Okay, the trouble with blue is the absence of red and near infrared. There's nothing wrong with blue.
Exactly.
It's when it's on its own. You need the balance of daylight. We've lived under blue light for the whole of humanity, and another 2 billion years before that. We've lived with blue light at twilight, and the problems are not really to do with blue at all. The problems are to do with the absence of red. We're infrared starved. That's our problem.
Yeah,
and that's only happened in the last few decades. So
yeah, I do think that Bob's model is unique, and I don't know of anybody else who's ever done it. And the fact that it just automatically popped up at 480, right where melanopsin is, I think is a serious consideration for the circadian people, whether or not they just got it wrong. And again, I totally agree with Bob that what we really did is we took out all the red and the near infrared, and then all of a sudden blue became a bad actor because it was really the only thing that was left to blame. But what happens with that atmosphere and the Rayleigh scattering and how that tends to distribute into the night, the blue, and the fact that we can sit underneath a blue sky at much higher levels than what you're getting from a TV or from an incandescent or an LED bulb or whatever, for 100 years and survive, should be telling people something, that blue's not the problem. So
I recently saw an article published by Martin Picard called The Energy Resistance Principle, and he presents this sort of foundational equation that energy resistance is equal to the energy potential over the flow squared. And he makes the case that energy resistance is an extremely important part of life, being able to contain energy within certain constraints so that we can use it coherently. And it makes me wonder about what we were talking about earlier, in that if you impact the flow, because the flow is to a power in this equation, it has a disproportionate effect as to the potential energy. And if you increase the flow, the energy resistance goes down. So you get basically better energetics when it comes to the mitochondria. And I think this is yoking quite well with what he talks about in this paper, in that what we're getting when we're outside is basically allowing the flow of energy to increase, and thus there's not excess resistance in the mitochondria that is, I guess, ostensibly causing aging in the end. Does that make sense? The idea of this energy resistance principle?
I need to think about that.
I'll have to send you the paper, because I thought it was really quite compelling. It made sense of a lot of different things in a very simple sort of principle.
Well, I think that it's very clear that mitochondria is taking advantage of the increased radiative component, as I guess is what I'd say. How you want to describe that in an simple electrical circuit, or whether you want to talk about quantum tunneling and quantum, various steps on the electron transport chain. I just think in general, I think what we're pretty well agreed on now is that there's KT, which is kinetic driven processes, and then there's a radiative that goes and comes in a 24-hour cycle, and those two are working together. When you put those two together, you have the maximum efficiency, I guess I'd say, of energy production, and which is a positive for health And like anything, the more efficient you are, I mean, nature, one thing's absolutely true. The more efficiently you do use your energy, translates into longevity, because you don't burn yourself out. So I don't know, Bob. You got any other thing?
Yeah, well, it makes sense to me, but I say I need to think about it more carefully. How you actually translate this. One thing I would say, going back to the difference between kinetic and radiative, I think again this is a very astrophysical thing because we think all the time about kinetic processes and radiative processes. Going back to the basic thermodynamics again, the heat engine, and I think we are a heat engine. We're a heat engine which operates on a combination of kinetic processes and radiative processes. If you take the kinetic process that we went through a little while ago, you have this difference between body temperature and your surroundings. And, typically indoors, this is a small temperature difference of, 10 or 20 degrees. If you go outside under a blue sky, the blue sky is very cold. If you measure the temperature of a blue sky with a radiative thermometer, it's about -50 centigrade. So as soon as you walk out, let's imagine a moment, you get up on a lovely summer's day and you walk outside and you sit in the shade of a tree so you don't get too hot because of the sun coming down. But if you look around you, there's one tree that you're sitting under, there's lots of blue sky around you. You're getting infrared light scattered from the leaves of the tree down into your body, which you use for metabolism, and you're able to radiate your excess heat and entropy to a surface which is at -50, not +20, -50. You have much more, thermodynamically, much more energy available to you at that point than you would ever have indoors. And this is why you feel so good. You walk outside and you have a lovely blue sky and you sit in the shade and you feel great. And you've got full of energy. You've got much more usable energy available to you than you would if you were sitting in an office. And, it's argued by some people. I mean, I was introduced to human thermodynamics by a very good and very old friend of mine, Mike Disney, who was professor of astronomy in Cardiff for many, many years. And he worked through human thermodynamics years ago and never managed to get it published because everybody read it and said there's nothing wrong with it. But so anyway, it was never published. But it's really, really very important. And I think, one of the things we're going to be doing is looking at the athletic performance for world records and so on, and try and reconstruct the thermodynamic environment within which these records are generated, because it may tell us a lot about when endurance records, for instance, long distance running, when you actually get the world records, because it'll be dependent very much on the thermodynamic environment of the runner. So running in the shade with the blue sky will be predictably very advantageous, and hot, humid conditions with direct sunlight will be pretty bad.
That's really interesting to think about. And I guess I just wanted to get a little bit more of a clear understanding as to what you mean when you both talk about high quality photons and low entropy photons. What does that mean in the context? And I also want to tie in this concept that you spoke about last time, Bob, which was processed food is high entropy.
Okay. Well, let's talk a moment about entropy. Entropy is a scary subject. Most people don't want to try and understand entropy, but it's really when I get up in the morning. Okay, I get up in the morning. I do my exercises, and I come downstairs and I get stuff out for breakfast. I like breakfast, and my wife and I sit down for breakfast. And we have fruit and yogurt and kefir and all the healthy things and so on. And then I get up after breakfast and we clear away. We have to put stuff in the dishwasher. We have to wash things up. And what you're doing at that point, you're generating order by getting all this food out and eating your food. And that's a whole process of feeding order instead of disorder into your body. You will make lots of disorder during the day as you use this energy to move around. But then in order to keep the kitchen in some kind of reasonable state, you have to put everything away. And that's a lot of hard work. And you're fighting against entropy increase. You're reducing the entropy of the kitchen by putting everything away. And it's taking energy. You're using some of your energy to put things away because it's hard work to reduce the energy. And this idea of eating nutrients that allow you to maintain the structure in your body. I've mentioned to you before. There's a great book which everyone who's interested in this subject absolutely should read. And this is by Erwin Schrödinger.
It's a classic.
It's a classic, okay, written in 1944. I'll just read you a sentence out of the foreword to this book, written by Roger Penrose. I won't read you the whole page because it'll take too long, but just a short paragraph. He says, writing about this book, he says, like so many works that have had a great impact on human thinking, it makes points that once they're grasped have a ring of almost self-evident truth, yet they're still blindly ignored by a disconcertingly large proportion of people who should know better. Now, you can guess who he's referring to there, perhaps, but how often do we still hear that quantum effects can have little relevance in the study of biology, or even that we eat food in order to gain energy? This serves to emphasize the continuing relevance of Schrödinger's What is Life has for us today. It is amply worth rereading. So read chapter 6 in this book about entropy, and you will understand, the whole subject will become clear to you. It's a beautiful, the reason he wrote the book at all was to write chapter 6 about entropy. And it merits careful reading. It's not very long. It's written in very straightforward language. There's almost no mathematics in it. I mean, certainly nothing of the difficulty of Schrödinger's equation in it. But it explains all of this. It's all to do with life is a low entropy cavity in a high entropy world. The universe is increasing entropy all the time. It's a huge reservoir of disorder, but it has these pockets of order, which are where life exists. And the whole process of life is making order out of disorder. And that's where all our effort goes, into making order out of disorder. And the whole process of biological evolution is to add layers of complexity to tune up our ability to make order out of disorder. So, life is a heat engine. It uses radiation as well as kinetic energy. But the radiation, coming back to the radiation for a moment, look at the sun that's providing the photons. The sun is at 6,000 degrees, roughly, okay? Outer space is at minus 270 centigrade. And we're somewhere in between. We're taking this flow of energy from 6,000 degrees through our bodies, creating order, excreting the entropy out to a blue sky, which is not minus 270, it's minus 50. And that huge temperature difference between the sun and the sky gives us huge amounts of energy, compared with the kinetic difference of 37 degrees to 20 degrees. The energy we get from radiation, the power that we get from radiation, even though it's not used as a direct energy source, it's hugely potent as a source of nutrition. Think of it as nutrition rather than energy. It's hugely potent at maintaining our body structure and reducing our rate of aging. We age more quickly when we don't have that kind of environment, when we live in a 20-degree environment all the time, and we don't see the sky, we don't see the sun. We just age more quickly. We get sick more quickly. We're more subject to diseases and so on. It's very simple. Once you understand that, we are a heat engine and we thrive on thermal energy and radiative energy, we absolutely need to get outside, because that's where we get these huge contrasts. We get much bigger contrast between our body temperature and our surroundings. And we also are subject to the sun, which is a huge temperature difference between the sun and outer space. And we're in the middle. We're feeding on the sun and we're radiating to outer space. It's as simple as that. It's the whole thing is in that concept of order, disorder, entropy, if you like, and the kinetic and radiative energy sources of us as a heat engine. And I do have this lovely heat engine, which I run almost all the time. I turned it off for the podcast because it does make a little bit of noise. Not very much, but it does make a little bit of noise. Okay, that's it. It's a Stirling engine, so it's a flywheel to maintain a bit of momentum, and it has a piston, two pistons. One is a piston which separates a cold surface from a hot surface, or vice versa. You have a temperature difference between these two plates, and the temperature, you exploit the temperature difference between the two plates with these two out of phase pistons. You see the one piston is going 90 degrees out of phase from the other one.
Yeah.
So you can extract energy from that temperature difference. And the bigger the temperature difference, the more energy you can extract. And you can heat this with the sun on top, and you can have an ice pack below it, so you get this huge temperature difference, and it goes like a bomb. And this is our body. This is how we work.
Yeah, and I think that one of the things that Roger just did another
Roger Schwelt, you mean?
Yeah, Roger Schwelt, where he took one of his patients and took him over and put them in that was not doing well, put him in the side where there was sunlight coming in, and the patient immediately started to feel better and all that. So I mean, we have all these indications that are sitting there. The young man that was fighting a fungus infection in the lung went out. And I just think that the more we can do to get people to understand that sunlight is intimately involved, I would argue that in a lot of cases, what the sunlight does in the atmosphere to generate various reactive oxygen species like hydrogen peroxide and ozone on a circadian cycle. Going out in that fresh air, you're breathing, as Bob says, there's tons of surface area in your lung. You're breathing in. It's like Mother Nature's Lysol. It generates it because sun generates that in the atmosphere at parts per billions level. Exactly the same levels that we're trying to combat by adding it, on cruise ships and things of that nature. And then at night, nitric oxide is released by the microbes in the ground. You sleep outside in a sleeping bag. That nitric oxide's coming in, having a germicidal effect as well. So, I mean, built on top of all this is the effect on, I think you can almost go and use a size scale and say, big effect on pathogens, because if not, we would be swamped with all these viruses, and if something wasn't killing them off. Then you hit insects, and we're having all this problem with pollination because of people are using not only blue lights, but even red lights some can have positive, some can have negative. They're putting red lights in beehives now for some extent, trying to do this. And then you get to animals, and then you get to humans. And, what I hope is that the more we explore, the more we figure out how to use light to actually, protect us in some ways. But if you're already dug a steep hole, like you're living in an enclosed space where you don't even have the energy delta to make yourself be healthy, people survive. I understand that, but we're not talking about that. We're talking about what are we optimally designed for. In some ways, those Indians down in Patagonia have a much better plan than we do. Is what I have a feeling, and yes, we have the advantage of all these drugs, but I'm not so sure that if we couldn't get light to be more a part of people's lives, that they wouldn't be better off. So,
Well, I think I've sufficiently had my brain melted and my worldview sufficiently changed by this conversation as well, which tends to happen whenever I hear both of you in conversation with one another, which is basically the goal. I think that's a pretty good place to leave it at the moment, unless you guys have anything else that you think is pertinent to sort of put on the books. I think we've covered a lot.
We beat the hell out of one another when you're not in the room.
I can imagine.
Yeah, but I would suggest that look at some of Roger's stuff that's coming out, and I think that the Huberman podcast that Roger did was really good. And then,
It's absolutely brilliant. It's so compelling. It's so compelling, the story. And I have to say, Glenn's very busy Glen Jeffrey is very busy at the moment doing experiments, but the experiments that he's been doing with people using, people living in windowless offices, the people have been typically under white LED lighting alone. The results of adding incandescent lights for them have been absolutely dramatic. Absolutely.
Yeah. Wow. I mean, that's, again, it's probably not that surprising to us, is it?
Well, not to us anymore, no. But,
Yeah.
People have to understand this. We've got rid of a resource which we were never aware of. That is this thermal lighting, I call it, infrared rich lighting, sunlight, oil lamps, candles, fires, incandescent light bulbs. We've just suddenly got rid of all these things and we're suffering the consequences. Look at the decline in public health has been dramatic. Mental health, physical health, expenditure on public health, all of these things have dramatically suffered over the last few decades, especially over the last couple of decades when the whole world is filled with white LED lighting. There's nothing wrong with white LED lighting, but the thing that's wrong with it is you don't have any infrared there as well. You just have to add that in order to make it acceptable. And it seems so clear. And the frightening and depressing thing is that the places where you really need this healthy environment, people who are really sick in hospital and living in windowless wards, or especially in intensive care units in hospitals, you couldn't invent more toxic lighting for intensive care units if you ran 50 PhDs doing the research to find out. It's as toxic as you can possibly get in intensive care units, and people have to understand that. People can't survive under those intense blue clinical looking lighting they have in hospitals. People think, oh, it looks bright white and blue, it must be really clinically excellent for you. It's killing you. It's lethal in the long run. Not instantly, but it's in the long run, it's lethal.
And it's sad because we've had so many indicators of breast cancer associated with street lighting, things like that. It's like there's such we've been putting together this petition to get rid of the 125 lumen per watt requirement from the DOE. Basically, if it stands by 2028, those of us who are trying to do anything with near infrared, and even the people that are trying to do circadian, are going to be out of business, and everybody's going to be sitting under the same bright blue 6,000 Kelvin light sources, because that's the only thing that can meet the DOE standard. Why did they do it? They did it because they were in a silo that said, we just have to do lumens per watt. That's all that matters. And I'm hoping we're getting quite a few people on the petition. The idea is that, maybe this will be one of those things where we start putting green under the microscope it needs to be. I'm all for green, but it has to be smart green, not dumb green, and so there needs to be, are you saving energy really? And B, are you helping improving the health of the individuals you're exposing it to? And unfortunately, that never happened with the DOE when they came out with these standards that literally they said, oh, we're going to do an experiment with 5 billion people. We're going to switch the lighting and see what happens. And that was the total level of thought behind the process. So hopefully this will be kind of like a test case for how we save the planet the right way. The other thing that was just amazed me is that they were talking about all the detrimental effects of the International Space Station on the astronauts when they came back. And, it's like, hello, hey, you want to talk about something you could maybe do different, try, At the present rate, I don't think any of the astronauts will get to Mars before they're dead, even if they can survive when they get there. So,
yeah, I think that's a really important point. And yeah, I saw those pictures today. Those people look like they aged about 10 years in the space of 9 months, which I guess, again, is probably not all that surprising to us, but maybe to the average person it is somewhat surprising. Well, I think this was a really productive conversation, and I think this message is only going to continue to grow. I think with people like Roger reaching many, many more people through the Human podcast, and it looks like that's going to continue to be a theme in these types of podcasts as well. So hopefully this continues to grow, and I can't thank you enough for coming on today and sharing some of your wisdom. I've got so many ideas I need to process now, and I'm sure everyone listening to this also does.
Well, thank you, Cameron.
Enjoy your time in Scandinavia. Get out in the winter sun.
Yeah, well, I've been trying. I have a funny story. I went out for a walk. We have this beautiful lake, and you can go off the track and walk in the forest. And one day a few weeks ago, I think it was 0 degrees, but the sun was out for the first time in many weeks. And I got caught with my clothes off by a local who thought I was in trouble. And he was calling out after me, chasing me down, saying, what's wrong? What's wrong? And I said, no, I'm just a weirdo who was taking his clothes off in the forest because I want to get a bit of sun. And he was very skeptical. He may have called the police after I left. But that's one of the things they don't tell you about when you're trying to be healthy.
Okay.
Yeah,
Cameron,
those are the
everyone.
consequences. Yeah, but thank you so much, guys. I really appreciate it.
Thanks.
All the best.
Thank you so much for listening. I really hope you enjoyed this one. I've left some links to some of Bob and Scott's work below if you'd like to learn more about their research. I've also left all of my links in the episode notes, so please feel free to subscribe and engage, as there will be much more content like this to come. Again, if you'd like to support my work, please consider subscribing to my Substack, as this is where I share most of my thoughts and insights that go beyond the scope of this podcast. This really helps me keep this going. So thanks again for listening, everyone. Take care.